Artificial intelligence is already transforming the communications, networking and services sector. And to find out how, I'm talking today with Bill McFarland, Chief Technology Officer at Plume, about how the company is bringing AI smarts to the communications sector. So, Bill, great to see you again. Thanks very much for joining us. Now, is AI an important part of enabling new services? And if so, what types of services is Plume enabling with AI?
Plume believes AI is pretty much critical these days for service providers to enhance the services they're already providing, make them more sophisticated and more capable, but also it enables sets of services that you really couldn't do any other way. Some of the examples are predictive network maintenance. So this has been a field for many years, but the sophistication that you can apply now with these new machine learning tools is much greater. So you can look at a long history of what's been going on. You can look across all the millions of homes that you might be managing as a service provider, and that data can all be piled together and used to do a much better job predicting which networks are having trouble, which customers are going to be dissatisfied, and so forth. Another thing that you can work on is predicting customer behavior. We all know that, when you go to a website looking for something to buy, that they're applying a lot of algorithms about what products they're going to show you. Is it the blue dress or the red dress or, whatever. In this case, you can look at what customers are perhaps going to call you for a service call. This is an area that Plume has worked in. And we're able to predict these customers are likely to be calling in the next 30 days for these reasons. Similarly, you can look at whether customers are likely to churn or not. Are they dissatisfied enough with the system such that they're going to disconnect or go to a competitor? Another area where we've applied very sophisticated algorithms is just in optimizing the Wi-Fi networks. It's kind of how Plume got started and a lot of what we're known for. It's become much more complicated and sophisticated with multiple access points in people's homes and many different frequency bands and channels to choose from. Setting that network up so that it works as well as it possibly can is a task that can't be handled by really simple heuristics. You have to have a sophisticated algorithm, something that really looks at all of the factors and brings them all together to decide what's the best configuration. Cybersecurity is another area where I think many companies, including Plume, are applying sophisticated machine learning technology. Here you're trying to learn how do devices normally behave. You're trying to detect anomalies. What's happening when they do get infected by a virus or malware? How do they misbehave? How can I detect that that has happened? So that's another area that automatic learning, there's so many different types of devices. You couldn't possibly do this by hand. You couldn't do it with just some simple heuristic. You need sophisticated algorithms. There are areas that Plume is working in having to do with finding motion. We use Wi-Fi signals that are going around the home to detect whether people are moving around the home. It can be used to form a security alarm system, or it can be used to form a wellness monitoring system. I can tell if my elderly parents have gotten up and had breakfast that morning. Detecting that type of motion using Wi-Fi signals is quite complicated. It works fine and it's nice. It's non-invasive. It's not as privacy concerning as having a camera or something. But it does require sophisticated analysis of these different signals. So for all of these new types of services and applications that Plume supplies, artificial intelligence, machine learning, sophisticated algorithms are necessary ingredients to provide those.
Okay, well, that's a very strong case for AI. Could you go into more detail about the use of AI in these new services? I mean, to what specific areas or algorithms is Plume applying AI within a system?
I think you can break it into a few different categories. So in the category of network operation and management, I talked about optimization. Here we're using a rigorous form of optimization called mixed integer linear programming. We take a bunch of different inputs and examine those to figure out what's the best configuration for the network in the home. We also are doing predictive analytics of network conditions. So, for example, when we do these optimizations, you want to do it in the middle of the night. But you want the network to be configured well for the peak time the next day. This all involves trying to predict forward based on the history of what's happened in this particular home. What are the conditions going to be like at a certain time of day, at the peak load time, etc. We use these types of algorithms to help ISPs understand, is what they're facing a power outage, or is it an outage in their own networking gear? So here you're looking at regions of where there is outage. You're trying to examine the patterns of that and understand, is this a power-related problem or is this a networking-related problem? And we have specific algorithms that we've developed to detect very specific problems. We have these things that we call evil twin and evil brother. These are where you have, in a single home, two parallel networks running. They might even have the same SSID and the same password. Maybe the consumer had one network up and running, then they got additional equipment, a new Wi-Fi system, and they set it up, and they thought they'd be clever and give it the same SSID, the same network name, and the same password. This creates absolute havoc in the network because devices roam back and forth between the two networks and often can't communicate with each other if they're divided among the two networks. This is another thing where we can go and automatically detect that this is happening in a particular home by studying the patterns of connections and disconnections of those devices. A whole other area where we're applying these sophisticated algorithms is in customer behavior prediction and management, predicting who's going to call in and what reasons they're going to call in for, predicting who's likely to churn, looking and analyzing how are people using different applications and different services on their devices. All of that can be done in a fairly automated way using these algorithms. And then the last grouping is analyzing device behavior. For example, we do sophisticated device typing. When Wi-Fi devices connect to a network, they don't tell you that they're a certain type of device. You have to figure that out on your own. And so you have to analyze the way they're interacting with the network, the types of messages that they're sending, the patterns of communication that they're using in order to identify that, oh, that's a Apple MacBook Pro, or that is a Samsung Galaxy phone. And similarly, some devices these days are doing what we call MAC randomization. This is where they randomly change their MAC address. It's done to try to enhance privacy, and it's probably appropriate when you're out in public, walking around. You don't want to have people kind of tracking you and tracing you. But on the other hand, when you're connecting to your own home network, you want to be known by that network. You want that network to apply the settings, the parental controls, the security settings and things that you've set up and that you desire for yourself. However, when the MAC address is randomized, it can be hard to identify this device that just connected. Which device is that, and what policies should I be applying? But using these types of machine learning algorithms and things, we can look at that device. Even with its MAC address randomized, we can tell by the way it's behaving which device it is, and thereby apply the right settings and controls to it. So all of these are fields. Another one, as I mentioned, was anomaly detection. So anomaly detection for cybersecurity. We're looking at devices. We're identifying whether those devices are having anomalous behavior or whether they're behaving normally. All of these are areas where these sophisticated artificial intelligence type algorithms can be helpful for service providers.
Okay, really interesting use cases and applications there. So these algorithms sound interesting from a technical perspective, but do they really make a difference for communication service providers?
We see significant improvements in throughputs, in the performance in terms of quality of experience of people utilizing these networks. We did a study where we looked at apartment complexes, and we looked at the percentage of apartments that had what we call a high pain index. This is where they have both a lot of interference and they're trying to carry a heavy load of traffic. Those are the apartments that are really suffering. And then we applied our optimization system to that entire apartment complex. Plume has a system whereby we recognize the clusters, the grouping of apartments that are interfering with each other. We can optimize channel assignments across that entire apartment complex. And when we do that, we can cut down almost entirely, cut down by about 90%, the number of apartments that are experiencing that kind of difficulty. Now, what that results in as an end result is an improvement in the relationship, really, between the service provider and their customer set. And this we've also been able to confirm by working with some of our CSP partners, and we've studied things. For example, in that study set, the ARPU increased by $5 to $15 per month. This is because they can sell these additional services. They can sell even premium Wi-Fi at an added premium. NPS scores increased by 60 points. Support calls were reduced by about 50%. Truck rolls were decreased even more. They decreased by about 67%. And churn, which is in some ways the most expensive factor for service providers, was reduced by 30%. And one of the things that this type of really robust system that's automatically configured from the cloud can do is that it can allow people to do self-install. You really don't need to send an installer to set up a mesh network in somebody's home. And that itself can save, like $150 per customer, not having to send a technician out to set the network up. So there's a lot of true net financial results that CSPs can count on when they work with this kind of a system.
So great examples there, Bill, and clearly a lot of benefits for the communication service providers there. Could you give us a concrete example of an AI system, how it works and how you went about building it?
Yeah, so I think I can highlight, for example, the optimization system that we use. It's kind of the core of Plume's activities with their service provider partners. The goal here is to configure a multi-AP system in a user's home so that it gives the highest possible performance. And it's more complicated than you might think. Again, as I was saying, you've got all these access points. You've got to figure out which ones connect to which, what the traffic routes are going to be through the network, what frequency channel each of the hops in the network is going to be on, where the client devices should connect, and which frequency band they should be connecting on when they connect to a given access point. Now, this process starts, in our case, by doing some feature engineering. That's very traditional in machine learning and these types of artificial intelligence systems. So the first thing that I described was that we try to predict what the conditions are going to be like during the most critical time of the day, when the peak load is going to occur on that next day. Because we like to optimize these networks in the middle of the night when everybody's sleeping, the network's not loaded. That way, if you have to reconfigure the network, it's less disruptive. But you don't want to optimize the network for the conditions at that time. There's no load, there's no interference from your neighbors. That wouldn't be effective. What you want to do is you want to predict forward what are the conditions going to be like during the peak time the next day and optimize for those. Now, after generating these predictions about what the conditions are going to be like the next day, we then combine that with a bunch of other input features. So we look at the interference levels that have occurred historically and make predictions about those, the traffic loads. We look at the signal strengths between all the devices in the home. We look at the historical achieved data rates. When devices have connected at a certain signal strength, what kind of data rate have they been able to achieve? We look at the capabilities of the devices. You might have a home which has a mixture of different access points. Those access points have different capabilities. They might be different generations. One might be Wi-Fi 5, one might be Wi-Fi 6, one might be a Wi-Fi 6E that has 6 gigahertz. Same thing for the clients. So we factor all of these different inputs into this algorithm. So then you choose a model or an algorithm. In this case, we're using this mixed integer linear programming model or algorithm, and we set that up. And the key in that algorithm is that it's going to adjust the settings in the network until you have maximized some objective function. And here we create an objective function that factors the throughput to individual client devices. It factors the overall system capacity in the network, and it factors the fairness among different devices. You don't want to get a high score on that objective function from just having one device have fantastic service and all the rest of the devices are getting very low throughput. So all of those factors are rolled together into this objective function. The algorithm works as if it were trying every possible arrangement, every possible combination of all of those factors, who connects to who, what the frequency channel is, etc. And out of that, it chooses the very best configuration. Now, the algorithm actually runs and finds that in a much more efficient way than brute force trying every possible arrangement. But it finds a true global overall maximum for that objective function. And when that's done, you get your outputs. The outputs are these decisions about the topology. We decide about channel bandwidth. Should we be using 160 megahertz channel bandwidth or 80 megahertz or 40 megahertz even? The channel frequencies that should be used. And we make decisions about where clients should be depending on their signal strength. And that's kind of complicated because as clients move around in the home, the conditions and where they should be connecting changes. What we want to do is we want to essentially create these tables where if the client is seen at these sets of signal strengths at the different access points, here's where it should be connected for the highest possible performance. And then these results that we've gotten are all loaded into the network. And they're loaded either as semi-static configurations. Okay, here is which access point should connect to which access point and the frequency channel that should be done on. Or they're loaded as dynamic behaviors. So for example, I described that when a client moves around the house, the phone in my pocket, let's say, it's going to be changing where it should be connected. In that case, what we're loading down is we're loading down thresholds and settings in the access points that allow them to dynamically adapt to the changing conditions brought by the client moving about. And so the end result is that we have a network that's configured to achieve the highest possible performance and to continue to react to the conditions. And in fact, that optimization, we can re-trigger it and redo the optimization if it turns out that the conditions are not what we were anticipating. So if the conditions are very different, if the scenario is suddenly very different, we can re-trigger that optimization and we can load down a new set of configurations that's more appropriate given what's actually going on.
Okay, incredible levels of detail in that system, really interesting stuff, and obviously that would make a massive difference to home and office networks. Now, if you were advising a CSP that's interested in getting the benefits of AI, what would you say to them at the moment? What would you recommend?
The first thing I would say is that you really want to be doing this in the cloud. The cloud has a number of real advantages. The first is that you get effectively infinite compute power. So these systems can dynamically scale up and down. They're big, heavyweight iron. This is serious compute capability when you do this in the cloud. And that allows you to use these types of sophisticated algorithms, whether it's a machine learning algorithm, something like a sophisticated optimization algorithm, really enables all of that. The other thing that you get is you get nearly infinite amount of data storage. One of the big constraints on an access point or some other type of networking gear locally in somebody's home, so these devices are all built quite economically. They have very limited amount of memory. That memory is usually already pretty much filled up by the applications that are running right on that device, just what's required to move data around in the home. So what you want to do is you want to take that data that you're collecting and move it up to the cloud and store it up there. There you can keep a very long time record. I can have a long history of what's happened in a particular home for when I'm trying to do these predictive analytics or understand what's going on in that home. I can also analyze the data in a horizontal way, as I call it. I can look between different homes. For example, if I'm trying to detect that there's a virus in a Nest thermostat, I can look across the 35 million homes that Plume is managing, and I can look at how Nest thermostats are behaving across that entire set. And I can use that to identify that this Nest thermostat clearly has something wrong with it. So that infinite data storage becomes very important. Another thing you get in the cloud is that you have a tremendous set of already constructed AI tools. We work on the AWS platform. There's other good platforms, but they already have a large number of open source, already put together packages and tools, libraries and things that allow you to very conveniently and quickly build these types of machine learning systems, these types of sophisticated algorithms. And then the last part of it is that it's really easy to update and train new models. Having to roll out new firmware to change some behavior or adjust what's going on in the home and roll that new firmware out and install it in the local computing devices, the local networking devices in people's homes, is problematic. And service providers really like to avoid that. There's a long testing cycle involved in it. There's always this scary moment of trying to update the firmware and whether something's going to go wrong. You can potentially brick the device. There's a lot of problems with it. If you have all of these algorithms operating in the cloud, it's much simpler to do a cloud software update, much more reliable, much quicker. You only have to update the software in one place. Again, you have a much better set of tools to do it and so forth. So all of those point you to doing it in the cloud. The other thing that you really want is you want to do all of these things on the largest set of data that you possibly can. Plume's really fortunate because now we're managing these 35 million homes, and we can pull all that data together and analyze all that data to see trends, to extract these behaviors that different types of devices have, to use that to identify rare devices. Maybe there's a device that only even shows up in 1 in every 100 or 1,000 homes. If you tried to identify that device using only local algorithms, it'd be pretty hopeless. But if you pull together the data from your entire deployment and use that, then you can identify these much more rare circumstances, whether that's a rare kind of device or it's a rare kind of network failure, for example. And then the other thing is that you can use these same input parameters, right? You're collecting a bunch of information down in the home and you're moving that all to the cloud. You can make use of that data for a lot of different algorithms and purposes. You can use it for network optimization. You can use it for maintenance, network maintenance, proactive maintenance. You can use it for customer relationship management. We're using it to identify things about the people who live in that home, right? By observing what types of devices they have connecting to the network, how those devices are used, what times of day they're used at, and so forth. You can actually come to interpret things about what that customer is like and what that customer would like. And so there's a great efficiency in getting this all into a single system and in a single place. And that allows you to have kind of single pane of glass management for all these different services, whether it's cybersecurity, Wi-Fi management, parental controls, all of these different types of services that are part of the complete bundle. You have one set of data that you can analyze, one set of management tools that you can use to take care of all of those services. So there's this just huge advantage to bringing all this data together up in the cloud and being able to analyze it.
Well, it sounds like it's a great time to be a data scientist at a communications service provider. Really interesting insights. Bill, fantastic to talk to you again today. Thanks very much for joining us.
All right, thank you.